the result of Atlas, which strongly with the measurement dots are the measurement of the width of the Z, which strongly suggests that there is only 3 families. Before that, I was in the UA1 experiment. You remember the UA1 experiment is the one which discovered the WZ boson, and for which Carlo Rubbia got the Nobel Prize. We were oscillating, we had something in favor of 3 families, but completely not excluding perhaps the first family. The big deal for LHC is the question of the mass. You well know that in the Standart Model, the particles are massless. All the predictions of the Standart Model are on this basis, but the particles have masses, and we have to ask ourselves from where it came. And this guy, who is now becoming well known, Mr. Pitt, but there are other physicists which receive also prizes for the electroweak symmetry breaking, and that is the holy grail of our community looking for it. And one of the things we certainly would like to understand, to hear today, is how have we advanced at the level of the fixed production. So the main questions of the Standart Model and behind are related with the particle masses those fixed boson provided. One of the questions to which we have answered. Are we really limited with the 3 family, or at the energy of the LHC could we see some more families? We have the question of the dark matter and the unification of the fundamental forces, which some models predict then, especially the supersymmetry. And do we have seen sign of the supersymmetry at LHC? That is also one of the parts of my presentation today. And all these questions, hopefully, will receive some answer from the LHC. So, beyond Standart Model, we have the question of the dark matter. This circle here and the separation represents what is our universe, only 4 to 5%. The dark matter part, which represents something like 23%, and the rest is the unknown dark energy, which for the moment appears only on some rare exotic models. The neutrino masses question, the asymmetry between matter and antimatter, the acceleration of the universe related with the dark energy, what happened at this scale. In fact, most of the models, and for that we built the LHC, predict that something happened at the level of the TeV. So we will probe all this model and so on. At the beginning, when we started to construct the LHC, and I am about sure that I already, you have already seen several times this slide, and especially from me last time when I came here, we thought that it was enough to push on the button of the LHC and the supersymmetry will come out. In fact, like it was predicted, supersymmetric particles should decay in many jets with large missing energy. So, producing light supersymmetric particles, many neutrinos, so large missing energy, many leptons. In a word, it should be very spectacular type of event. I have to confirm before showing the result, which will be only unfortunately limited, we have not clearly seen much of such striking events. The other question went with the peaks. We saw also by pushing on the button of the LHC that the peaks will show up relatively immediately, and in fact you will see from my results that we have still limits compromising mass region for the observation of the peak, but not yet really clear evidence. This plot was established in 2006, so our dream is somehow a little bit seriously some kind of doubt starting installed in our mind. But the LHC is properly working, and at the time we push on the button on, we already observed the huge set of standard resonances. So you see that after a few hours of the LHC running, after a few days, you see the significance of all these classical Standart Model resonances were appearing, and you see the beautiful high-level resolution we have. We clearly separate 1s, 2s, and 3s states of the upsilon here, and even see the old omega phi from the old time when they were discovered at in bubble chamber physics. I am personally at the beginning bubble chamber physics, the time I made my PhD. And that represents only 20% of all the data we have on tape. So before going into the results, some kind of forward I wanted to present to you here at the beginning. So the year 2010 and 2009 and 2011, 10 and 11 were very successful. The LHC was very well working, and Atlas and CMS collected something which was not at all imagined at the beginning. 5 times more what the people from the machine predicted to us at the end of the year. 5 times about -1. And with that, we could make some analysis of for the research of the Higgs boson in the Standart Model, and we found some limits. I will came to that later on. In RP conservation, supersymmetric environment, we have not seen clear evidence for supersymmetry, and are only putting this kind of limits for quark and gluon. We also look with a huge interest into high mass resonances, and that is the limit at to which we could access with the 5 femtobarn inverse luminosity statistics. A lot of models were predicting relatively sample models, and we look for them in the effective mass in the region of few TeV. I have also results for that, and I will show them to you. Some deviations start to appear, but not very convincing, and certainly not statistically significant. So the Standart Model, our old Standart Model, reigns supreme in the proton-proton collision at 7 TeV for the moment. Some other general considerations, but all the reasons for building LHC are still there, because one important task is to measure well the scattering cross-section of WW, but it's not yet well achieved. We have few tens of this type of events, but not sufficiently statistically large to really study the region of 1 TeV. And of course, we don't know yet, we will see the result in one moment, that the Higgs doesn't exist, but if it doesn't exist, it's certainly a big discovery. Because most of the people have to, especially theoreticians, I think you are the majority here, you will have to go to your desk and to find the explanation. The SUSY, we are still looking for it. We have poorly looked for the moment due to statistics to what happens for the heavy supersymmetric quark tops and bottom in the third generation. The extra dimension have produced about half of the 100 papers I was mentioning before, but we have still to continue. Perhaps found some new gauge looking for leptoquarks, some fourth fermion is still on the way, and so there is still a lot to be done and remain tuned. New results, especially from year 2012, with even more increasing the luminosity, the statistics will certainly provide new things. At least I hope, and I am sure you hope too that something new came out. And for the moment, the only window in which the Standart Model Higgs could lie is this one between 115 and 128 GeV. You will see in one moment how we have achieved this place. So now it's the menu of my talk. So heavy ions, Standart Model measurement, Higgs searches, beyond Standart Model searches, where is SUSY, is too much for one single seminar. So you have some menu, like in the restaurant, and it's up to you to choose from where I stand. And after a decent time, I will stop, of course. Yeah. Sorry? Oh. Till 5 is fine. Okay. So I will try to do my best. But let's say that I start with the Higgs searches. So you have time to think about the next place you could receive. So I don't go into detail of all the branching ratio here. That was very nicely made by Alexander Korchin talk last Friday, and that is how loop one event came in from the collision here and producing two very hard photons. So you have no charge tracks here in the tracking system. All these gold lines are the charge particles produced in the collision, and you have very, very high energy lattice photons. And when you reconstruct, you can, by measuring the angle at which they produce, you can easily compute the mass. So in principle, if we see a lot of events like that, one thing that is simple, you will see in one moment that it's not so easy, not so simple as that. So all through that, this production channel, proton producing Higgs, decaying into two photons. The other very powerful channel is the Higgs decaying into two Z bosons. One of the Z being in our research on its mass shell, and the second one being out of the mass shell, decaying into 2 leptons. And here you have the image how it looks in the detector. So you have 2 high energy electron measures. The energy is mostly deposited in the electromagnetic calorimeter. And here, in this case, the Z could also decay into quarks, of course. You have 2 jets, whose mass is related with eventually either a Standart Model channel or from 1Z decay. That is another case where again you have 2 electrons here, and you have the other Z potentially decayed into tau, for instance, because you have some energy deposited here in electromagnetic calorimeter, but you have also energy in hadron calorimeter, so very likely this charge track is here a pion, and the second, the fourth object is somehow hidden. And so these guys are waiting to discover something. And let's wish them they are still in life when the discovery came, because very likely a ticket from Stockholm could be sent to them. Let's at least wish that to them. So that was the Higgs situation at the summer this year in the conferences. And let me take a few minutes to explain to you what it is. So here we compute the confidence level of what you observe, the sigma here, and what Standart Model predicts for all the known channels. So for the moment, all the results on the limit of the region where the Higgs could still be is a purely mathematical approach related with the probability to observe something compared to what the Standart Model predicts. So at the summer, if you are at 1, so what you observe agrees with what the Standart Model predicts, or less, because you have a certain number of hypotheses in the background prediction for a given channel. So, in fact, what is expected is this dashed line here, and the color here indicated the 1 sigma dispersion of this expectation and the 2 sigma dispersion of this. So, but if you are above, so all what is below 1 corresponds to a very low probability of Higgs of production in this region. If you are above, you have some hope that perhaps something exists here, and at least you cannot exclude this type of event. So at the summertime, with relatively only 20% about of the statistics we had at the end of the year. And the next, my result will be on the full statistics we accumulated in 2011. That was the window in which the Higgs boson could lie if it was live, and that was the limit if the Higgs boson was heavy. One of the big experimental problems which came with the accumulation of data, you have more data because you have more collision provided by the accelerator, and you see that in the slot of time you register your data, you have in fact many collisions at the same time, so superposition of the events. You can imagine how difficult from experimental point of view it is. And we have up to 20 reconstructed vertices, collision vertices. We reconstruct it, in fact, with the charge tracks which are produced at this point. But, for instance, for this channel, you have no charge track. So you poorly, either you very well measure the angle of production of your photon, or you can mistake. You can associate the photon to not the right production vertices. And that introduced you about a factor 2 in the resolution on the map. But okay, that is the life of experimentalists. And we try to find always the best way to came to that, to the result. So this slide summarizes what was also very nicely in the talk of last Friday by Alexander Korchin, are the production processes of the Higgs, and that is for the LHC, and that is for the Tevatron. And you see that here, that is a cross-section of production of Higgs plus something. You see that here you are 20 picobar, and here you were at the Tevatron 10 to minus 3, and that shows you the big potential of the LHC data for the finding of the Higgs. So that also what was in the Alexander Korchin talk, the different decaying channel and branching ratio compared to each of the other for the research of the Higgs. That is a product of this cross-section times the branching ratio. So you have some channels which are highly produced, like for instance the Higgs decaying to B bar B, but it's not so easy to catch this thing. And the Higgs photon, you see it about 3 orders of magnitude below that. So again, here the life of the experimental physicist is very difficult. This table summarizes all the channels we explore for the moment for the Higgs search. So in the low mass region, that is directly related to what you have on the previous plot. We look in photon-photon, the gold channel of the Higgs decaying into the 2Z and going to 4 lepton, the Higgs going to WW, and the decay of the W being into 2 lepton plus missing energy, and so on. That are the background channel which has to be considered, and the cross-section for most of this background channel is much, much higher, to 2 order of magnitude higher what as the production processes here. That are the mass ranges for these different channels, and that is the luminosity. So you see that CMS analyzed for the December seminar, that was presented at CERN in the middle of December. Atlas mainly analyzed the most promising channel, like the Higgs to photon-photon, 4 leptons here, and the channel WW, but not yet on the full statistics. So only that is a full-time seminar. So I have selected the most promising channels, and I will show you 2 to 3 slides for each of them, and how we succeeded to get the limit I was mentioning to you before. So,
are those mass ranges the ones that you studied, or the ones we cannot exclude?
that are the ranges of masses which I showed to you here. We studied. Let's say that the cross-section, let's take photon-photon, the cross-section in this region is high enough to be to make that Atlas and CMS are sensitive to this region. Out of this region, the cross-section is too small, and with the present amount of data, we cannot access it. Okay? So, this channel has relatively high production cross-section and branching ratio. So how it looks in the detector? You have, for instance, that is an example, a muon and a second electron here in this case. So relatively large electromagnetic energy here in the electromagnetic calorimeter, and detection of tracks and measurement of its momenta here using the tracking system and the muon system here. And you have missing energy. So that is typically a counting experiment. You cannot reconstruct here the mass of the system because you measure the missing energy, but only in the transverse plate. So you make some selection requiring that your lepton is at least 15 GeV, has some property of isolation to be sure that it's a lepton. You reject as much as you can background coming from Z being here in the background, Z decaying in mu and electron, and you have some requirement in the opening angle here, delta phi, between the two leptons. And by applying these different cuts, you reduce your amount of events in the study for something like here 10 million, no, 100 million to something which is few hundred here. And with that, so purely accounting reduce your sample of events in consideration. So here in color you have most of the background from Standart Model which are considered in this research. And you plot your points, the number of data you observe, and you don't see really deviation for the moment. You put all these things in a mathematical box, you shuffle it, and you get this response score, which say that in between this mass and this mass, at a certain level of confidence, the Higgs is not there. But in this region, you observe a little bit more events as what came from the Standart Model background, and so you hope that between here and here you exclude. If you in this that is observed range, and below 128 there could be something from a production of the heat. Another very promising channel is the Higgs decay in TZ and the Z going into 4 leptons. We call that the golden channel because if we succeed to measure precisely the momenta of the energy and the energy of this lepton, we can reconstruct a mass. And so to reduce the background, we first make some cuts on the mass of one of the two T candidates, and another type of cut on the second one, and you see that for the second one, we are very far away from the mass shell. We even push it up to 12 GeV. How this type of events look in the detector? You have 4 high energy tracks. You see 4 more than 40, 26, 20 here charge tracks. In this, that is a for muon event and sign of muon production in the muon chamber. that is a mass spectrum, the full mass spectrum. We have in total something like 72 observed events in the full range here. The expected number from the Standart Model is at the level of 75, and you see here the number of events with the errors coming from the background and the number of events coming from what is observed. There is a small excess, but with this type of excesses, we cannot tell anything about the discovery. You can imagine. And now if we make a dilatation of this mass plot and taking only the low energy region, here you see that the number of observed events is 13. We expect 9.3. So in this low mass region, there is some striking production. You have, for instance, 3 events between 119 and 120 GeV. Statistically, certainly not very significant, but okay, if we include the statistic and if more events are found in this region, the resolution, I had to say from experimental view, the resolution is at the level of 3 GeV, so something, an accumulation of events in a very narrow region could be relatively promising. So again, if you put all that in a box of mathematical box and you compute the probability, you exclude some region, or what here is below 1, that is the full region and that is the low mass region. And you see that again here below something like 128, you have some promising, perhaps, observation for more statistics. So we exclude all these mass regions. And that is what is expected in this region, and that is what is observed. So again, we have something which perhaps could indicate that a region where the Higgs could be. The third channel which I wanted to present here, it was the Higgs through gamma-gamma. And part of this plot I will show, Alexander Korshin already showed the last Friday here, but I will give perhaps a little bit more comments about the experimental way this thing was obtained. So that is my first indication of the two very high energy you see here, 86 GeV, 56 GeV, observed in the electromagnetic calorimeter. And here I prove to you that in this mass region, our resolution is 3.5 GeV. So very high level precision for the observation. But you have a huge photon background. The nature is not very kind for us. Photon cross-section is high. And you see if we have something in the region of 120 GeV, it poorly deviates from the prediction from the background. And to have this small Gaussian curve here, the amplitude has been multiplied by 100 to make our eyes more visible. But it's not as high as here, it's relatively straightforward. And again, here we compare the observation to the production, and you can see again that below 130 GeV, 127 here, you have something which could be a sign of the production of He7. And that is with the full statistic of CMS. And in one moment, I will show to you the result from Atlas. So that came from the status report asked by the Director General of CERN on the 13th of December. And that is the result of CMS, which excludes all the mass regions between 127 to 600 GeV. And that are the results of Atlas, who have again some features in another places, but typically they exclude all what is below 112.7 to 115.7 and some other regions. I will came to that. So that is expanded to the low mass region. And I have taken this plot from John Ellis' presentation with his comments. So there is something interesting around 125 GeV, both in CMS and in Atlas. CMS see a relatively broad enhancement. Atlas typically prefer 125 GeV. Another way is always mathematical, and using all the channels, including the one which I have not presented in detail, is to compute the probability that what we observe in the data is not true. So that are the CMS results. So the probability that what we observe not being true is relatively low at the level of 10⁻², something like that, around 2.5, 2.6 sigma. And in Atlas, it's a little bit above 3 sigma, what they observe at 125 GeV, and that is with the full statistic of 2011. So, John Ellis concludes of that there is interesting things around 125 GeV in both experiments, but could be also 119, why not? Anyway, 119 to 125 is not far from each other, and we have seriously to check the estimation of the energy in both experiments and try to converge eventually to something in common. So that are in detail the results of Atlas. You see in fixed to gamma gamma, in this region they have a small deviation. That are the data of Atlas to 6 to 4 leptons, that are the distribution of the points in the region between 119 and 220, where CMS has 3 and they have only 1 here. And that is 6 to WW count to next experiment. So, in summary for Atlas, that is the significance in photon-photon, the significance in ZZ, in WW. If you are allowed to combine this, statistically, you came to something like 3.6 sigma at 125 GeV, but they refuse themselves to claim that they have discovered the peak, because it could be also a statistical fluctuation. CMS treats their data, the different channels which were analyzed and which are listed here in another way, putting in this plot the ratio sigma over sigma Standart Model, where you should have 1, and the bar error indicates the dispersion of this result. And so you see that all of the data within 1 sigma fit with 119.5, but fit also relatively well with 124. And if CMS combine all that, we are at 2.6 sigma. For the moment, we have not yet combined Atlas and CMS to see if we can say something more. So the only window for the observation of the peak, as we have obtained it from the LHC present data, is between 115.2 or 7, I don't remember, and 127 GeV. So very, very narrow mass region. What can indicate that our good Standart Model could be valid up to the max. And if you allow me to make the step after that, that perhaps nothing exists behind the Standart Model. Of course, there is a lot of other questions, the unification, the antimatter, the mass of the neutrinos, the hierarchy and dispersion of the masses. For sure, there is a lot of things which the Standart Model, for which the Standart Model has not any answer presently. But it's still not sure that the Higgs is in this window. Perhaps next Christmas, now the machine provides statistics we have by a factor at least 2. It's a hope, perhaps to have even more, or if there is a crisis somewhere in the machine, we can have much less. But let's be positive and hope that really we will have a lot of statistics, but definitively we should have the Higgs discovered if it exists, or not discovered. And then we have to find something else to explain from where the masses to the particles came. For the moment, the exclusion is about, it could be above 600. So I am back to my restaurant menu. Sorry.
When we are waiting to get the combination of this and that last, because it's very interesting to see how this accessibility level.
What I know and what you know also certainly, and many people here also, that the two groups have a common group to combine the results. They are on the way. I don't know if it will be for the winter conferences, which came in a few weeks from now, or in the spring conference. I am sure that at least for those of you who will go to Australia, the next huge conference is in Melbourne, there will be a combination. And perhaps new additional results coming from the 2012 data. People are working, but you see, it's not easy at this level to add two experiments. Even if they are looking for the same, the technical problem, detector problem are not exactly the same. So, which plate would you like to use now? So, Leonie.
First of all, I would like to thank you for the excellent presentation, excellent talk and excellent presentation for the research results. My question concerns the channel classification to gamma.
Yeah.
We know that historically, once upon a time, a decision was made by CMS to choose from the two versions of the CNRS electromagnetic correction. And the decision was taken to choose the version of the collider consisted of crystal, very fast crystal, very expensive, extremely expensive. And this is a distinctive feature of CMS.
Yeah.
So we would expect that CMS would manifest a better resolution, better result for Higgs to gamma compared to Atlas one. But right now we see about the same. How could you comment on that? And my second question is, what do you think these results would look like if we had the Ludwik type collider instead, which you were involved in?
Yeah. So first point, the crystal. The crystal research development were performed in your department here. Some scintillation group involved into scintillation development and progresses have participated to the definition of the quality of this lead tungstate crystal. They have not been produced here because a department or even a laboratory has not the full capability, full industrial power, but they were produced in Russia. And now to the question why CMS is not much better at Atlas. The response is relatively simple. First of all, the resolution we are getting, 3 GV over 120, so it's a resolution of better than 2%. That is already a big achievement. Why Atlas is as good as CMS? That came from the fact that they measure, to estimate the effective mass of two photons, the major, you need to know the energy, what is good for CMS, very good for CMS, thanks to the crystal, less good for Atlas, but Atlas much better measure the angle between the two photons as CMS. So finally we say, worse precision on the energy and a better precision on the angle. Atlas and CMS are about at the same level of precision for the mass of gamma.
And the second question, what would happen if the decision was made in favor of Ludwik? How these results would look like?
In the case of Shashlik, the energy resolution was at the precision of Atlas calorimeter, and we were foreseeing a fresh shower in front of this scintillator calorimeter, providing a measurement, angular precision measurement of the type of Atlas. So we were about as good as with the crystal, and it would cost half the price, of course. But the people at the time were thinking that the Higgs came much more easily as the reality. And they think that with a very luxurious and strong car, people think that they go faster with a less sophisticated and smaller car. But a small task, and especially if the speed is limited. And here the speed under quotes is limited by the background and the experimental conditions. You have to know that one of the big problems is the material of the detector. The photon or the electron interact with the matter situated before the electromagnetic calorimeter, and that deteriorates the precision of the measurement and the quality of the electron or the photon. So there is a huge mixture of technical problems which are not so easy to solve, unfortunately. And as experimentalists, we are trying to do our best, but nature is not so favorable. Susie, you would like to have... So, the promising of Susie is related with the unification of the interaction. It's an elegant way to solve the hierarchy problem of the Standart Model. The light Susie particle could be the best candidate for dark matter. So when this Susie well supersymmetry appeared on the market of the model, it was looking that the nature should favor something like that. I don't go into detail of that. I don't know if, Alexander, you presented a little bit. You also had in your seminar a global view of SUD. So we are looking for many jet events, and that is not too difficult to find in our data. We have very high energetic jets produced, but that is not the only thing you have to discover the peak. So I skip this slide and I let you go back to last Friday presentation of Alexander, how the peaks appear, image of the Standart Model particles, and how the decay looks like, and the lightest particle, neutralino here, could be a good candidate for the dark matter. So, we started, of course, with relatively simplified models. We have not explored the 19 parameter plane where SUSY could be. So we started with the simplest one and looked for a limit on quark, on gluon, and for the moment this plot only cover the data of 2010, 35 picobars here, and they doesn't include all of the theoretical uncertainties. But that doesn't explain the antimatter question and some other questions. So, Perkin conclude, we must be confident the possibility that we have came to the end of our ability to understand physics microscopically. So we have to perhaps invent something more profound, more deeper to consider the understanding of all what happens in particle physics. But as you have seen, I am not at all expert in physics, and I was sure very well February. February. So here again, I am not expert at all, but I will show you in our group at Ecole Polytechnique, we have two physicists who are involved in CMS on the heavy ion, and the results are very promising. So what happens, you have two lead ions which goes each to the other and slowly produce something which seems to be now well admitted, a quark-gluon plasma state for a given time, and that has a certain number of consequences to the physics, and at least in the observation we have sign of that. You have to imagine that we have up to 6,000 particles produced in that. That's the detector work. You see one event here. So you have several thousand, 5,000-6,000 charged particles here. And for about all the calorimeter channels are fired. So we have huge activity, but as well as Atlas CMS detector works well and produces data. We were very happy in 2011. We produced something like 60 times the statistic of the previous year. So we have not, that was taken in fall, November, beginning of December, so we have not yet the results from last year, but even the results from the year before are very, very interesting. So the motivation for that is a study of the quark-gluon plasma properties, and the first sign of this state was coming from the quarkonia system. So the quarkonia were studied very deeply in the US and also in the previous CERN experiment. But now I think the temperature certainly increases with the rising of energy, and we hope to access much more data. And you see the instability here in energy for these different states that are the quarkonian states, which allows to probe all this data. So one of the striking, so what I have here, I have to prove you that the detector is working perfectly well. That is the effective mass reconstructed in the lead collision for 2 photons, and you see you reconstruct it very well. So the detector works very fine. That is the G-psi reconstructed on a background which is not so high. So the sensitivity of the observations that are jet measurements, and we are reaching transverse energy of the jet at very high level. That was in 2010 up to here 400 GeV, what was never observed until then. So the first measurement deals with the number of charged particles produced per unity of pseudo rapidity. So that is something which is not so surprising, but the increase as function of the particle number, and here is the estimation of particles as function of pseudo-rapidity. As this property is increased with the number of particles, that is not so much surprising. other property in measurement of the heavy ion collision are the dn of the eta and the energy production per unit of pseudo rapidity. So you have results, and you see how it changed. Here you have the square root of the nuclear energy in the collision, and here you have the dE over d eta, and you see the point obtained with CMS here, how it's huge change here in the process compared to lower energy experiment. That is a plot, a propaganda plot, which shows that the detector is performing well, because we observe the upsilon, the G psi, very nicely, and even for the first time in heavy ion collision, the Z production became into lepton. And one of the most striking, important observation of the 2010 data which came out is the comparison of the production at the upsilon, in the upsilon mass region, is the disappearance of the upsilon 2s and 3s state, which, according to the specialists, is a proof that some kind of gluon plasma certainly exists, and that this state vanished somehow in this plasma. That are the observation results, and you see that the depression here to the 2s plus 3s compared to 1s is at the level of 4.3. That is one element of the ZK in the heavy ion, so you can in muon it's much easier as in electron, but now we have also evidence of the speed production in electron position. So imagine that you have here 5 or 6,000 particles produced, and you need to extract the mass of the Z, so very performant. So that are the latest results. Some partly the data of 2011 are used here. The peak of the Z and in muon and in electron are relatively well defined. The background here in electron is much higher, and that is due to the difficulty. So the energy loss of the electron is what I was mentioning just before about the problem of the quality of the electron energy measurement. Another very striking result of the lead collision was what the people currently call, I don't know if it's the right term, is the jet quenching. If you trigger on one jet at a relatively high energy, here 120 GeV for instance, and if you look, this jet in proton-proton collision will be produced in most of the time with a second jet which is completely back-to-back to the first. That is standard QCD. And here what you observe, in fact, is that the second jet is much lower in energy, by a factor of 2 up to 3, and that, in the jargon of the people working in the domain, somehow the second jet is quenched. The energy somehow is dispersed in the quark muon plasma. So again, I am not expert on this, but have other or even better explanations about that. Another interesting question which came out of the lead-lead collision is the problem of asymmetry. So if you plot the variable here, the PT of the jet 1 compared to jet 2, that is related to the quenching, and you normalize it to the sum of the energy of the two, transverse energy of the two jets. In proton-proton, it's distributed at 0 with a certain dispersion. In lead-lead, depending from the centrality of the collision, you observe that at full centrality, you have no more this feature. You have an unbalance. So apparently that is also some kind of indication of an effect due to the quark-muon plasma effect. And that is a plot which with a variable here. I will not go too much in the detail of it, but one tries to estimate when the energy of the second jet, which is not balancing the high energy jet. So the important thing here is this red area here, which indicated high energy component of the jet, high energy track, as function of particles inside the cone and outside the cone. So you see that outside of the cone you have everything in positive here and nothing in negative inside. So that indicates that the energy is relatively widely dissipated out of the jet cone. So it goes everywhere, like if the quark, some kind melt in the gluon quark plasma. That is another measurement of a variable which is a nuclear modification factor. And that again indicated that for central collision, and you have a minimum here around 10 GeV, and which increase for larger PT. And that implies some strong constraint on the pattern energy loss. Unfortunately, it's for specialists, and I am far from being one. I'm sorry. So that is also one of the striking results from the lead-lead collision. So in fact, at CERN there is one dedicated experiment, ALICE, for the lead-lead collision. It came for the moment out that CMS at least has good results, and sometimes even better as ALICE. And that is related also with the quality of the detector we needed for the proton-proton and the search of the system. So that is the plot of again RAA, how the energy of the quench jet is distributed. So you have some dissipation, some kind of dissipation of energy larger at the level of half, 50%. So strong quench for light hadrons here. Colorless probes, I have taken that are suppressed, but I cannot tell you much about that unfortunately. I'm sorry. I am at the end of what I have tried to extract for you for the less that, and back again to the menu. That is now 10 past 5.
How can they accelerate less ions?
How? There is a process, in fact, which takes out all the electrons of the lead atom. It's the same procedure as for photons. The photons are coming from hydrogen, and you strip the electrons. So you do the same for the lead atom, and you strip. This machine can accelerate every ion. If you have a source of that dedicated ion. What is not so easy and you cannot be produced in many places. You have a chance in France, in Grenoble, at the Commissariat of Energy Atomic, which is a place which is able to produce sources of lead. There was a question.
The beautiful J-size mechanism for construction is fast. Do you see the J-size suppression? Known as, why don't you show this?
That was something about the proof last time. I have it certainly in all the documentation which are on my computer, so I can find it for you if you want. But I have not included it here. But you see, at the beginning, okay, chip size suppression was something not so much important to rediscover.
It's one of the signatures.
Yeah, of course. It's in the data, and there is a lot of work on the Quarkonia and several publications on the Quarkonia, which are now in the journal already. But the people from heavy ion were pushing to have data on the same energy as the ion for photons. To be able in the same experimental condition to compare what happens in photon, and in opportunity to that, we are sure that what we observe for the G-size suppression and for the epsilon suppression is completely proved as well. In fact, if I well remember, the suppression of the G-size is even a little bit more suppressed as what was with the increasing of the temperature due to the increase of the energy.
The D-photon spectrum was supposed to be excess photon.
Yeah.
And, well, could you...
In the big...
Yeah. Could you specify in terms of the angle? I mean, well, because the background should be supposed to come from quark-to-quark channel annihilation, right?
Yeah.
And it is dominated by the small angle. So the question is, what is the restriction on the angle, first of all? Is it to the central barrels or also to the end caps?
That is certainly considered. I have not in my mind the angle, the minimal angle which...
in terms of rapidity.
I don't have the... I can again count it for you, but I have not really...
More than one radian.
Of course. Yeah, of course. No. The limitation... We are limited if the two photons are too near to one or the other, and you have seen how well we measure the mass of the pi zero in photon or the eta in photon, and the limitation in angle, small angle, with is fraction of degree, something like that. because the size of the, so for Atlas, for instance, they have...
The statistics also include small angle plots.
Yeah, of course.
But then you have extra background, whereas the signal from Higgs decay is supposed to be isotropic, basically, whereas the background is dominated at small angle. So you import...
in the production, you mean? The production, you mean?
Production of...
No, but...
And it decays isotropically, it's stellar anyway. And it's produced mainly from zero fusion with rather small source moments. So
yeah, but the being produced isotropically, you cannot cut in some region of angle. You can, I am sure that the way this background was produced, we had a cut on small angle or pi angle to reject the maximum of the pi zero and other production processes.
Pi zero, of course, it's smaller.
Yeah.
But
It also low mass and mass resonances have relatively
the
small
next
angle.
question is whether you will actually be able to measure the angular distribution for the decay of Higgs to check if it's a really scalar particle.
We need to measure this angle, of course, to check that it's a scalar. Yeah, of course. That is one of, but for that we need statistics.
I also have we are hearing from everywhere that the main channel for searching Higgs, the primary channel, is decay to bigger bar or tau.
Yeah.
And now you are presenting something which I thought to be something like a secondary channel. So why abandoning
secondary channel at the level of the branching ratio? But you have to consider that the decay in B bar B has the huge background to beat from QCD production, with QCD will produce to you also B bar B. And the ratio from QCD production to B bar B is 5, 6 order of magnitude. So it's a very difficult challenge. We are looking for it. For the moment, I don't think we have presented results, but somebody are looking for that. Is the decay in tau plus or tau minus. And that is also a channel which we are studying in our group, but the data are not yet sufficiently performant. But because the tau is also difficult, you have a neutrino. So you cannot so easily measure the mass. It's again a counting experiment. So
in the combined plot there is also the channel with neutrinos when one of the Z's decays to 2 neutrinos.
So this channel is also studied when you consider one of the Z in 2 leptons and missing energy. That this one is considered in all the list of channels we are looking for, but this Z2 neutrino is at the same level about as the other, let's say, golden channel. Alexander.
No. We are automatically transformed to this question. But before that, I would like to say thank you very much for Ludwik for nice report.
Only partial report, because on the menu they were...
No. Now you can to do question on all problem of
I don't have infinite time because Professor sorry? Tomorrow morning. Okay. I have a small duty at some time, I don't know, in 15-20 minutes. The students from the high school nearby here wanted to have some kind of initiation to physics, and I have prepared to them in French in addition. Apparently they are learning French. Found few one which will join you